Is there a point? It's done? Yeah, okay. All right. Boy. Yeah, okay. This is actually another project which I'm going to talk about. A lot of involvement with the NASA and Air Force. I could say this is not exactly an undergraduate project. A lot of graduate students, PhD students went through this. Actually, a lot of my PhD students were involved one way or another in this project. And it started actually with my PhD studies back in the 90s when I was doing the PhD work at Notre Dame, University of Notre Dame, in the US. And so my advisor, Professor Dassi, is world famous acoustician. Is recipient of the Aeroacoustics Award for Embry. Very few people like that. Very famous for his studies, particularly on gas interactions. This acoustics of gas interactions, all kinds of his work with the Professor Goldstein, who wrote the book Aeroacoustics, very famous one. So it's actually, he was the chief scientist at NASA. Lewis now is Glenn Research Center. So they work on the development of the second order unsteady aerodynamic theory. So what the second order unsteady aerodynamic theory means is beyond what we know about steady aerodynamics or it's computational techniques. Basically, it tells you if you have an airfoil and the airfoil produces loading to the camber and of the tail, then there's features which very much affect the interaction of the disturbance field with the flow, like we have again turbulence interacting with the wind, like this is the case. So there's a process called rapid distortion, which happens when this disturbance gets very much distorted as it approaches the wing or the airflow or blade, anything like we're doing this right now as well, rapid distortion theory. And this affects pretty much the response, aerodynamics. Okay, so this second order effect actually very critical. And so that was a part of the work which I was doing to develop the gas generation technology for the CFD, because it's not an easy process. And how you develop the gas. And that's what this talk is all about. So we'll talk about some applications. And first start with the formulation, motivations. So we developed what they call momentum source model. I did all this back in 2006-07 was the first attempt to do this for the single time harmonic. And then in 2011, there was the first paper which was appearing on the extension of this single gas to the entire turbulence, because the turbulence is basically a spectrum of energy which is composed of modes. Each mode is basically a time harmonic gust. You basically assemble them in a special way to represent specific spectrum. Like for instance, in the atmosphere, for instance, when you look at the turbulence, like in the clouds, etc., that's basically would be typically following some uncommon spectrum. It's a specific type of energy spectrum where all the modes are distributed in a special way. If you do turbulence in rotor-state interactions into machinery, like for instance, turbojet engine, that probably would be mostly useful. It would be like Lippmann spectrum. In some other cases, the easiest one is Gaussian. It's the easiest one because it's actually very easy to model those things. The other one requires a bit of tweaks. So this modeling process is actually also involves some other steps, which I'll talk about, which is basically broadly called random flow generation process, RFG, random flow generation, because a lot of statistical data there, a lot of like stochastic processes involved. You will see a lot of tensors, a lot of other things like that. So that will be the challenge. But anyway, that's what it takes. And then we'll talk about applications. So one application is what historically was unsteady aerodynamics and acoustics of gas responses for the airflow, wings, etc. And more recently, it's what we're doing with NASA. It's a turbulent urban vertical environment. That's a classical example where we apply the same methodology, which I developed for 20 years, 15 years ago, for this new kind of things, for the eVTOLs, future air taxis. So, but it's all basically for the simulations. It's all methodology for high-fidelity simulations, so it's implemented in several CFD codes, including BLPTI, open form, fluid. It's now part of this. It's basically, I think it's also part of the GitHub. So you probably can get it from there as well. So ask the students. Historically, again, the urgent need for this type of source in CFD simulations came from our analysis for the micro vehicles. That was part of the Air Force work, which I started in 2005. We were very much interested in developing these micro vehicles and the need to analyze what their dynamics of these micro vehicles will be. And they needed to see how those micro vehicles will behave in a very gusty environments in the cities between the buildings. Kind of the same task that we have now for the eVTOLs. Totally different scale. eVTOLs is big. Micro vehicles like bird. It's like really a moving stage. Could be even talk about this. Could be even some insect flying. So next day when you see the cockroach, somewhere, it could be a small vehicle, which is basically a spy vehicle. That's what the Air Force. In fact, we would go to the Air Force Research Lab, and there will be in every pole there will be everywhere displays, and they'll be showing this future. Just scary future, right? So you cannot go anywhere. Everything you see, like a bird sitting on a branch, it's actually a micro vehicle, because they look exactly like that. Because the whole idea was to put them exactly looking like small birds, but then at the same time they'll be not just like watching. It actually can have a weapon inside. So the typical picture they always showing that, and then this display there would be like this guy that sits on a branch, could be the whole swamp of them, small things coming into the city. Sits on the branch and then see what's going on and see the bad guy, which he identifies somewhere in the window in some apartment, and then he'll flying. And that's it, guys. Now that's what they were showing everywhere on displays. You're just wow, passing through this thing. That was a scary thing, and yeah, it's fun. I was just doing pure aerodynamics. Had nothing to do with other things. They were doing a lot of these things also. All right, so a lot of research has been done on this kind of environment, gas environment, particularly. I mentioned before, I think in Japan was a lot of research done. So they did a lot of experiments on so-called prism flows. So they'll put the wind tunnel, there's a prism, some kind of brick, and they will be putting the flow around, and they measure all these structures which appear like cavity zone, separation zone, rotation zone, horseshoe vortices, all kinds of things. Actually, that was historically the project which brought about this whole subject of rapid distortion theory, which I was mentioning, how the gas gets distorted due to the mean flow variation, distortions, because the original work was done by famous professor Julian Hunt. I think he's not just Julian Hunt, he's Sir Julian. He's an English Imperial College in London. And so he was actually, I met him, he's a very peculiar person. Very interesting. But talk to him, it's probably maybe the same as talking to Einstein or something. He's one of those geniuses. You just see right away. Anyway, so he developed this whole theory for this kind of flows. Actually. That was the whole idea about buildings and everything. So it's actually appeared in the Journal of Industrial Dynamics, Wind Engineering and Industrial Dynamics. That's like one of those journals, if you have a subscription, you have to look up for, because a lot of things which I'm talking about showed up in those journals. That Journal of Industrial Dynamics and Wind Engineering. We call it Wind Engineering Journal. That basically, they talk about, usually it's like for civil engineering, particularly important because they talk about loads in the buildings due to the winds, on the bridges or any kind of structures. So that's an important journal for them. But of course, we like aerodynamics as well. So it's like one of those areas where we intersect. like aerospace engineering and civil engineering, this is the area we intersect very clearly. That's what you mentioned. Some people work on this next year. So, anyways, so depending on the prevailing wind, of course, you have changing direction and different structures appear on both sides. Anyway, so for us, what's more important because it's all chaotic, and even for us, for the problem right now we do with NASA on the vertiport heliports, on rooftops, it's very chaotic, turbulent. So for us to analyze those kind of effects on the structures, like blades or wings, etc., we usually decompose those things in canonical forms. So one of the ideas, and that's what I was doing, you can decompose the structures like this into the forms of time harmonic gas, sharp edge gas, Taylor vortex, particular turbulence things, etc. So there's some kind of canonical forms, because then later we can analyze them separately. Like for instance, if you can decompose, I can understand what happens for the gas interaction for that particular frequencies, which I including with this kind of decomposition with the structure, with that blade, etc. So that's much easier. Otherwise, it will be no control. You want to create some sort of controlled way to analyze things. So that's what. So that's what we actually do in NASA research. I was proposing from the beginning we need to do this decomposition of the flow fields in canonical forms, and then we study a response to each of them. They're going to assemble them back. That's the more sort of coherent way to do this. So anyways. And that's again an example which we were doing for this type of buildings. That's what Ali Reza was my student. He's doing is going to be modeling, and I've talked about this briefly before, but I'll talk more about this thing later. With this particular problem. So this is a lot of things happening here at the rooftop, right? And that's where this things will be landing, taking off from. So I feel that. Anyways, so you can pretty much build the structures using SPOD, cross-spectral thermal composition. I can do FFT as well. So I'll have another presentation tomorrow where I'll talk about two various approaches. They actually should produce more or less similar results, but the SPOD sometimes is much more expensive to do these sort of cases. So anyway, running LAS quad-J simulation and proceeding with the SPOD, we can look at those structures which appear different parts of the flow around the buildings. And for instance, we can associate like one particular spectrum with one particular structure here, should be one carbon shading, another structure somewhere further downstream. And then this guy will get shaded with this shading, which we'll call gauge and stability moments, which is due to the separation at the edge of the building. Which again produces this Kelvin constant stability, and that shows up in terms of the structure, which is pretty much time harmonic gas. So that has specific frequencies, you can see. That's what it can float right into the model for our analysis. So this is the decomposition, which was basically we followed. So there will be another lecture tomorrow, I think, on the SD7003 airfoil, directing with canonical forms. So that will be all focus of this thing later. Well, for micro vehicle research specifically. But this thing is actually just talked about how it goes. So we have the sharp edge gas model. There's a Taylor vortex model. There's a time harmonic gas model. Synthetic turbulence model. So those things are the structures which we sort of can predict response. In fact, that brings it to the problem where we can actually train the data based on the position. So we know already how we should react to each of those models. We can assemble for anything in the end very quickly. So future that will be probably machine learning thing, which is useful for other pilots to react. Okay, so this is a paper. Historically, it was one of the first in 2006. I think that's where the whole model appeared first. 2006, 20 years. Boston. So this is the classical time harmonic gas, two-dimensional in this case. Usually it has what they call the transverse gas, which is equal to the chord or like two-directional flight. Then you have the chordwise. You see the variation, this chordwise direction, which usually produces much of the effect on the boundary dynamics. For transverse gas is most important. Yeah, that's basically induced angle of attack. So that's direct link to the unsteady loading. This gas is more like dynamics of the boundary, so it has like indirect effect. And then there's another component which is not shown here in the board, which is called spanwise component. So that's all produces what's called oblique gust. Now, oblique gust, like spanwise, is not shown here at all. We're not talking about this until, oh, maybe no, we'll talk about this very well, because that will be the work of Marina, our PhD student, was wife Peter, another Russian student. She was doing her PhD on that three-dimensional, and I'll show you some of her results there. But this is a classical two-dimensional time harmonic gas, and that's what we implement for a variety of different studies usually. And the idea is actually how you generate this gas. So this gas is generated in some particular area upstream of the surface. Could be like airfoil, wing, it could be rotor. Now I'll do like Vadim is doing rotor. So some sort of source model, right? And so there's magic involved. So this magic is some particular analytical work which was done using complex functions. Cannot do it otherwise. So with the complex analysis, you can generate the specific form of function which will produce a source for the momentum, which will generate a particular gas of that particular amplitude, frequency, etc., etc. And then the turbulence. So it's the same, because for the turbulence, you just put them all together, different gas, in a very special manner. So I'll talk about this. A legacy of this work again is coming from the so NASA used to arrange famous CA. CA stands for Computational Aeroacoustics. Computational Acoustic Workshop. There were like 4 of them, different years. In 2000, 2004, I think it was another one in 96. And so the gas airfoil problem, what is called Category 2 benchmark problem. So NASA would put benchmark problems like this. There was many, like 6 different categories. And within each category, there's something else. So there's many problems. And they would put them as a benchmarks. And the way they operate is that they, for instance, announce the workshop, people who want to try with their own code. So that was all about code development, right? So you develop your code, there's different, we talk about different methodologies, right? Develop the code, so they give you this benchmark, you run the results, you produce solution, and you submit. And then the judgment day comes at the workshop, because then it's a secret solution, which is not. But nobody knows. When we, like all different teams, prepare solutions, some send it, and then people come and learn, you know, how miserable we are. So that's actually why they probably stopped doing it, because after 4 workshops, people were so like maybe somebody committed suicide or something. I'm not sure, but you can imagine you come and then your solution is just miserable compared to the real one. So your code is just bad. So you like look at your because they put everything like here's this guy, here's this guy, here's that. And by the way, Joma's always like one of the best. They would cut DLR, like Joma and NASA would come and they usually produce one of the best solutions. Now we also had pretty good results as well. Now there was also a problem, by the way, that also might affect why they canceled it. This because, for instance, some people, famous guys like my advisor Tasi, there's another famous guy, Chris Tam. There was a rumor because we actually produced one of the benchmarks. So we were one of the ones who suggested the benchmark from our group at Notre Dame. And so there was a rumor that Chris Tam somehow figured out the solution. He learned from someone about the solution. And so he actually got the result right just because he already knew what he was getting, right? So of course it's always easy to get something where you know the solution. You can adjust certain things. Anyways, it's called fudging. And see it again. So anyway, and then they wouldn't talk to each other for 10 years, you know, after that. Like they were just hating each other. So that's people say, okay, that's enough of that. So they stopped doing this, just not to basically traumatize people. Because it's really, you know, very upsetting. If you can imagine, you can develop your code, you get the solution, you come, and then wow, your code is not doing things right. So working on those. But in a sense, why this also workshop is important, not only that you prove the concept that your code is working right you got the results. But if your code is really good, what happens? You get all the money, you get all the grants. So if you submit the grant, of course, people know you got the best code of the best. So money goes to you from NASA, from Navy, from everything. So that's how a lot of universities were developing codes. They were doing this thing with the hope that the codes are excellent, most accurate, and they get the grant stuff. So there's a lot of things involved. So anyway, there was a lot of issues there, both political and realistic. But that's where the GUST airfoil problem was one of the main benchmarks. That's why people were really looking into this issue also for that. But of course, it's also very good. That's how we model the unsteady wing loading, right? So when you fly and you experience this GUST, you know that you have an unsteady load. And also unsteady rotated direction, rotated direction, because that's actually where my PhD dissertation was on rotated directions. And that was about like on state of fan struts, in turbofan engines, which is high bypass engines, the main source of noise is actually fan noise, no more jet noise. Used to be jet. But turbojet, do you guys take jet propulsion classes? Do you know what the different engines are? Like turbojet, turbofan, something about them? Anyway, you know which engines we fly? Like when you fly on Airbus or Boeing, do you know how they called?
Turbofan.
Huh?
Turbofan.
No, not just turbo. Turbo is for everything.
Turbofan.
It's a turbo. It's high bypass turbofan engines. It's like bypass ratio of 7. So most of the air goes through the bypass. Like only like small portion goes through the actual turbine. Majority of thrust is generated by bypass, not by the actual jets. In the core, they call it to machinery core. Anyways, in any case, research was actually about the interaction. Say fan and struts, which produces the turbofan, the fan noise. It's like 70% of all noise of the engine. So when the thing is flying, most of the stuff is produced by turbofan, in terms of noise. And it has specific directivity. You can see where most of the noise is coming in which direction. Jet is different. Jet produces other directivity. And that's how they measure. They can isolate different sources, etc. The jet noise is, because of this bypass now, it's much subdued compared to the ones which were like in the 50s, 60s. Because we started with the turbojets. That's what the original engines were, right? There was no bypass. It's turbojet. And military is still flying, but military mostly flying these days what they call low bypass turbofans. So it's still bypass fan, but it's a low bypass means that most still goes through the core and through the bypass. Because you also have to do the afterburning. And they ignite the jet very high speed. They need a very high speed jet. They ignite for the afterburning when they want to get that extra thrust. It's all about maneuvering, very fast maneuvering, all the jet fighters. So that's where they use all these things. So everywhere the gas problem is really important. That's one. It's a very big thing because in practical applications for the jet engines, it's all models the wakes behind the rotor interacting with the downstream stator, or fan wake interacting with the struts. And that's what produces 60% of all noise, or 70%. So that's big thing. That's what people model that. And the gas airfoil problem is the most baseline benchmark problem, where everyone is just trying to compare against and then so on. So some legacy of this work again for the high intensity gas airfoil interaction was Morse and Inger. You can find this is like classical self-interaction and change of energy, differential higher harmonics. I did a lot of work on the high intensity gas, but its amplitude was really high. You have a lot of distortion in the results because of the high amplitude gas triggered instabilities in a viscous way, and then we did a lot of studies in 2001. That's when I started my work more or less. Beginning of my career as a professor, that was pretty much the work I was doing for like 5 years. And then I went to the Air Force in 2005. That was kind of continued. But that's originally was the work with NASA, because NASA was giving us money from a special fund from chip scientists at NASA to do the studies, and that's what we did. So you see all this called diagram. Directivity diagram of switching directivity. for the airfoil gas interaction, typically dipole. If you remember last time I was talking about Volkswagen-Hawking's methodology for acoustics, which is basically a solution of light field equations, acoustic analogy equations, convective wave equation, and that basically you have the monopole, quadrupole, and dipole as results in the front field. That's what you usually measure in terms of acoustics, one of those three. So monopole is usually produced by thickness displacement, by the airfoils or the blades, etc. The quadrupole is all turbulent stuff, wakes, etc. And then the biggest one is usually dipole, which is this. This is dipole. That's produced by unsteady loading of any sort. Anything with unsteady loading. That's what gas produces. It produces unsteady loading because it has variation of the angle of attack. So use angle of attack is varying. Produces unsteady loading by variation. And then when you change the amplitude of this gas, you can see the distortion of this dipole pattern. That was my works in 2002, 2003. So at that time, I was looking how do you do this kind of, how do you impose the gas in CFD? We originally were working with the BUS code, which is the NASA code, developed by my friend Ray Hickson, who's actually works as a professor part-time at the University of Toledo, and then it's American Toledo. That's great. That's University of Toledo in Ohio. And then there's also NASA Glen, which is also Ohio, Cleveland. So he was like going back and forth also, probably hour and a half every day. So it was distance. So he developed this code. This is like one of the genius guys completely because he would wake up at 4 o'clock just to go to his garage and work, whatever. He works on the code. Well, he was developing the code sometime. All people like, but he developed this NASA code called BAS, which is like flagship code for NASA, particularly for rotor-state interactions. It's called broadband something simulator. I forgot the name exactly what it means, abbreviation. But the bottom line, that was his one code. Then he was working on another code, which is 4-dimensional CFD. It's time-space CFD. It's like Einstein theory that I think applied to the CFD. And so he was developing this code sort of like in his spare time, so that he developed his company, which he thought he would sell this code. I don't think it happened. But the thing is that he was spending hours and hours every day, like for years and years, to develop all these codes. And at some point, I remember there was a story. The code originally was written in Fortran. You know these different languages, right? Fortran is pretty old, right? So that's but most of the codes, most of the research code are written in Fortran, believe it. And actually, there's still versions of the Fortran which have been updated every year. So they still use them. Don't think like it's you like ancient something if you use Fortran. Of course, a lot of people moved to C++ later on, so that C++ was really a big thing. And then, so at some point, he decided, okay, I heard much about C++. Let me take the time to rewrite the entire code with tens of thousands of lines. Rewrite the whole code into C++ now from Fortran. So it took him a year. It took him a year to rewrite the code, and then he was running on the benchmark, and he found C++ is worse. That Fortran, original Fortran was better. So that was actually quite a bit of a surprise. So we're still using Fortran versions, all the codes. But that he was like a hero for us, for all of us. He took one guy to rewrite that spent the whole year to rewrite the code and find out that it's not really any better. So it actually works. There's a lot of things in C++ which is not as efficient as in Fortran for that particular applications. See, that was the story. So anyway, so we worked with him on this code development for this for the gas environments. We actually have quite a few papers together. We woke up in the AAA journal paper together, etc. And so several. And then so he was usually imposing things on upstream bound because nobody knew how to do the source. So you typically what you do in this kind of situation, you have a big domain, right? You have some kind of object here, like airfoil or boat or whatever. And your upstream domain, where the flow convects from, like wind flow, you have to convect this gas. Because gas is a convected feature. So it's convected by the flow, like turbulence, it's convected. Everything goes with the mid flow, right? So it's connected by the mid flow. So you have to impose an upstream boundary and then let it convect until it hits and interacts. Because you cannot impose upstream, like right upstream. So when you do this thing, what happens? You have such thing in numerical scheme and CFD called dissipation. So, numerical dissipation is really bad, but that's unavoidable. It's always there. It's always there. Then it depends. I mean, but you have to put this far field far away. Because the thing is that your boundary should be far away from the thing, because typically when you have acoustic waves of getting outside from the structure, they hit the boundary and they reflect back. And you have what's called spurious contamination of your results. Typically it will kill your solution very quick if your boundary is not very, 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 very far. We have to put it sometimes 100 cores away, so that finally this thing will dissipate back and get killed by itself in kind of dissipate reflection. So, or you put the buffer zone or something like that, right? So you have different ways to do this, the special buffer conditions, non-reflecting boundary conditions, basically. So anyways, it's always a bad thing to put at the boundary because it's far away, because you need to kill reflections. So if you put the gas there and then let it go, during the 100 cores, pretty much you will have nothing to be interacting with the structure. It will all dissipate. So that's not, so people were dreaming how we're going to get this gas sitting right next to the surface, like developing this model for the source. That was for many years before. So we did this. This is actually how it looks like for 2D. Now, the first guy who did it for 1D was actually the guy from Brussels. He's actually has been arranging in the last 15 years. He was arranging the last benchmark workshop. That was the workshop on the landing gear acoustics, which is kind of crazy. But that was a benchmark program where everyone would do this, like landing gear acoustics with a double gear. So it was a lot of like turbulent stuff. Crazy. But people were doing this thing, and he was local. Actually, I think his last name was previous slide. Yeah, local. So he was a student of Philip Morris. And Philip Morris is one of those big geniuses in acoustics. One of the, again, got the acoustics award, etc., etc., from Penn State. So this is the team from Penn State, was Philip Morris and McLaughlin, two guys. One is pure computational acoustics, and the other is pure experimental acoustics. Two of them formed the group in Penn State, but made Penn State famous for acoustic research. But they both retired now. I'm not really sure. Hopefully they're still alive. They should be as old as my advisor, who is like around 85. Anyways, so they from the same generation, very distinguished, very. Anyway, so Lockhart was the first one when he was a student of Morris, developed a 1D gust. It's a complex functional analysis. And I did for 2D and then extended to 3D and then extended to full turbulence. So that's how it looks like. This is a magic thing right there. Don't know what to say about it. Just magic. Anyway, so that's been well, now there's many pages of formulas. You have to get to this formula through many pages of analytical derivation using complex functions. But eventually that's how it looks like in the end. It's almost like E equal to MC squared, right? Like almost like simple as Einstein. Almost. Like nothing as simple as Einstein and CFD or in aerospace engineering. We still, although you can say that Joukowsky formula is almost Einstein. It's leaf equal to rho B gamma, right? That's it. Very simple. Almost equal to MC squared. Anyways, everyone familiar here with Joukowsky formula, right? No? You don't know Joukowsky formula? How many of you know Joukowsky formula? Like lift formula? Only two guys. That's only, I mean, you know how to predict lift, right? That's a lift formula. That's a lift on any kind of aircraft. It's lift equal to rho V gamma. That's it. Very, very simple. You need to be, I mean, I was teaching for many years, aerodynamics, steady aerodynamics, a lot of aerodynamics courses. Apart from jet propulsion course, which I teach as well, and advanced jet propulsion and CFD, everything in the propulsion and aerodynamics, you know. So yeah, it's you should know Joukowsky formula. I was born in the city of Joukowsky. The city was named after him because he's those guys who actually developed the whole aerospace science, get together People knew how to fly, but they didn't know why they fly. Nobody could quite explain what's going on. So he was the one who derived, also going using complex functions, by the way. So it's a good idea to know some complex functions. Using complex functions, you can derive the formula for the lift, which is very, very simple. Lift rho v gamma. Gamma is, but then you have to explain what gamma means, right? It's Pandora box. Yes, and in fact, lift production on the airfoil is magic. It's very different, by the way, for subsonic versus supersonic. Very different origin of lift. Okay, that's another thing you need to know. And the subsonic is actually what they call the concept of static vortex, which is very important. In the supersonic, it's all Newtonian momentum. It's different. So, anyways, you need to take a class in aerodynamics.
I'll ask the same question in Spanish. ¿Cuántos de ustedes han visto la fórmula de Golubev? Presentación y toda la circulación por hacen la mano.
So yeah, the same two guys. Oh, not more. Now people who can.
Yes.
Okay.
Why do you make us look very bad?
Okay, good. I was almost scared. Yeah, Nils Zhukovsky is kind of like a must. Because that's a steady aerodynamics. We're talking about unsteady aerodynamics, acoustic and steady dynamics. That's built upon these giants, like Zhukovsky. That's the brick, like the original brick, then the next thing. Okay, so if you need to know what the original brick is. Okay. All right, so this is the formula. This is actually the source which is developed. So you put it on the right-hand side of your momentum equation. So you know Navier-Stokes equation? Yeah. You know? I'm a bit scared. All right, Navier-Stokes, hopefully. Yeah, it's the fluid dynamics, right? Equations. That's what governs fluid mechanics. So this, when you put, so this is momentum. There's momentum terms, right? There's first is continuity. Then there's momentum. There's also energy and stuff. Blah blah blah. There could be many terms, depending on yourself. But momentum is always there, like 2 or 3 equations, depending on 2D, 3D problem or 1D, one equation. But the right-hand side is responsible for forcing. So that's why this method is called volumetric-force. So you put momentum in a source region, which is volume, inside the domain, where you force the thing to produce that particular gas with that particular amplitude, frequency, and then the turbulence of this particular scale. That's all basically forcing. Force it with the momentum on the right-hand side. Source. It's force, right? So that's what it is. And then you produce what's called incompressible disturbance field. Incompressible convective disturbance field. That's what it is. It's also divergence free, so it's a lot of details there, which again, in unsteady aerodynamics, usually we talk about this, what it means, like what are the turbulence. Turbulence is pretty much convective, incompressible disturbance field, which is usually divergence free. So that means there is some particular relationships which exist between the amplitude of velocity in each direction and the, say, wave numbers. Because you cannot produce like arbitrary disturbance field. Nature specifies what exactly should be the relationship. That's through the what they call the what the name of it, dispersion relationship. So dispersion relationship comes from the, say, divergence free condition. So there's a lot of things there which be satisfied. In fact, that's right there. This actually specifies this how the amplitudes are produced through this kind of disturbance. This is the one. Yeah. That's divergence free disturbance. So the amplitudes in the wave vector, this is the wave numbers, right? They should be in a special relationship like this. And that's nature based. That's typically what happens in nature. So if you're trying to impose some arbitrary velocities and arbitrary things, it may not satisfy the criteria that nature imposes. So you'll be violating this criteria. So everything when you impose it should be put together in a special form. And so this is a special form which you generate. Like in this particular amplitudes and wave numbers, etc. That's what you generate, and that's a source term which produces this. This is velocity field. It would be gust, or the similar harmonic of this is gust. When I have multiple harmonics like n or like n to 100, 200,000, no matter, that's how you generate the spectrum of turbulence. Okay, by superimposing these harmonics. But again, in the superposition process, how you arrange these wave numbers and amplitudes is not arbitrary. It should follow the nature laws. That's like divergence-free conditions. So that's what is all done. And then you have the some functions which produces what we call the limit functions. So basically, if you have the source, you cannot just abruptly go from like something to zero. You cannot do that. You have to be very gradual. Why? Because if you do it abruptly, you produce a huge pressure wave. As soon as you have this abrupt change in velocity. So this pressure wave will kill everything for you because it will be like more of a pressure disturbance rather than vertical disturbance. Because this is produces vertical disturbance, vertical disturbance. That's the gust. Gust is vertical gust, always. So vertical gust is convective vertical gust. But that can produce a pressure wave if you have this abrupt change. That's actually another acoustic problem. So this there's a very interesting interchange between acoustic waves and pressure and verticity waves, because everything can be decomposed. It's back to the Krishnan and long time ago. They were basically saying that any disturbance field could be decomposed in terms of potential, rotational, and entropic, which is a temperature disturbance. So in flow field, which we have, particularly to machinery, we have both, all three. And then you have to deal with each of the separately. So this one produces so the wake is a vertical disturbance. So that's the one. The wake behind this like airfoil, a blade, etc., or turbulence, that's a vertical disturbance. And that's what generates this kind of vertical disturbance. So generate pressure disturbance, totally different approach, totally different. So that's what it is. Anyway, we have created the region. So this region is done in a very smart way. So you see there's many subregions. So if you have N, you have N subregions. They overlap. In each of the subregions, the size is lambda over 2, the half length wavelengths of this particular disturbance, like each mode. Half of the wavelengths of each mode is specified in the region, and they overlap for different harmonics. Then they produce a spectrum, they right boundary of this source when they start convecting towards the structure. So this is how it's done. It's a very peculiar mechanism for using like this. 2011, when we finally published this paper called A New Approach to Modeling Airflow Interaction with Upstream Turbulence, where this particular method was finally announced for the first time. And now they celebrated more and more. Every student comes and they add something else. Now we have this very sophisticated like methodology there, etc. And it's published in GFM, Journal of Fluid Mechanics, just like 2 weeks ago, or 2 months ago. So fine, like so many years to test, right? 15 years to get it finally, like big job. And people use it now. I just recently got the paper published by Chinese, which is like knowledge thing. Now Chinese everywhere. Honestly, used to be. I was always reviewing AAA papers for the conferences, and I remember 10 years ago there would be like a bunch of papers from China. You would look at them now, just nothing. You reject them all. Yeah, but now when they come, pretty serious, very serious papers. Yeah, so a few of them were mentioning this methodology, so now they use it as well. You see, it's interesting, but aeroacoustics is now probably least supported in terms of funds and grants in the US. Almost nothing. Most of the support is probably China. And like, I don't know. Europe is much better than US. So a lot of things going on in Europe. There's European Commission projects, specifically on acoustics of this. So they have a lot of money on different projects, acoustics program in Europe. Used to be the opposite. US used to be. That's why we used to have all conferences in acoustics were always in US. Then they started to do like one conference in US. I don't know, 2 conferences in the US, 2 years, and then 1 conference every 30 years in Europe. Now they move. Each year is on the list. I'm sure that there will be time that all conferences will be somewhere outside. Well, maybe there will be 1 every 3 years or 4 years in the US. Yeah, it's a bit of a strange thing. But yeah, funding for our acoustics research is not so much. Also, consortium. We have the acoustics consortium in US. It's pretty much governed by like big companies like, well, NASA probably supervises, but there's GE, Pratt & Whitney, all the big engine companies. They give money, donate a bit money to create a fund, which is basically distributing money to the grants to some faculty, but it's small. It's really not big. Okay. So this is the methodology. That's what we're going to use now from now on. How would you read the source for the turbulence, for the gas, both 1, 2, and 3D. And remember, the classical problem is a single 1D transverse gas. So that's a component which is vertical to the core, which produces the upwash major leaf. That's called Sears problem, because there is analytical solution. That's we always compare against for the flat plate with the transverse gas. It's called Sears problem and Sears solution as a function for that. So that's usually the benchmark which everyone compares. At least you have to compare with result because it's analytical. In this case, for the flat plate. So this is a process where you do a lot of validation. So you can generate like momentum source right there, and you push this gas, so it goes like this France, like statistic France, right? And this is how this function is actually developed to make the smooth transition, so you can avoid the pressure wave build up. There's still some pressure. Typically, this pressure is produced as hydrodynamic pressure, so it decays very fast. There's different types of pressure, by the way. There's acoustic pressure is the one which propagates to the far field with the speed of sound. And there's a hydrodynamic pressure, which is also potential disturbance field, but it decays very fast. It's called evanescent wave, so it decays very fast. So typically you produce hydrodynamic pressure. It still can corrupt to a low degree your solution, especially near the surface. If you have very close, it still will be impact. But if you do this kind of smooth transition, the impact will be much less, and you almost won't see it. It will be some kind of pressure, but not much. So it will not be dominant. So, and then the gas momentum source, you can see here in this momentum source, you basically superimpose, like for instance, 4 different frequencies with wave numbers 0.7, 1, 2, and 3, and they all have this half widths, right? Half lengths, wavelengths. For this guy, this source region. For this guy, this source, this, but they overlap, and eventually they all meet at the right end of the domain. So this is an example for the 4 waves. And now we just basically looking into this how this behaves, and this is 3D. That's what Marina was doing. Okay, so you have this both in this direction, but also in spanwise direction. Generate this in spanwise as well. So there's wavelengths there. So you can do that. So you see, that's what she was doing. We call it line plus. So see, so this is analytical gust, right? And then the blue one is what we're trying to impose, and the green one is what we actually generate by this methodology. And you see how they match. So that's actually what we do always for the proof, that we actually generate what we want. The same thing for this spanwise gas, and this is a quadrilateral spanwise. Yes, one gas generation. You can see how it looks like. Even if, okay, so this is what they call, remember I told you dispersion relationship, the nature imposes divergence free condition on nature. It means if you generate 2 disturbance fields, 2 directions, you still will be generating something in the third. Even if you think it's 0, it's never 0. Nothing is 0. It's like try to push some, like with a spoon, try to push the fluid in one direction with your cup of tea. You'll immediately generate something in the other direction, even if you don't want to. It's there just because you always have this coupling nature for this dispersion relationship. So it's always there, nonetheless. So you put it in this way, but it's another one will show up. So that's why we want to generate the 2-dimensional gas, and this is 2 dimensions are dominant, but you also get something small in the other direction. So in standard board. So those things you have to be aware of. So these are the disturbance which created with K12, K20, A10, A21, and Mach 0.5. So there's 2-dimensional disturbance in the Mach 0.5 flow, which is convecting this whole thing. 2D gas generation, some range. And again, this A dot K should be 0. That's divergence free relationship. That's what imposes. They cannot just arbitrarily take those things. You have to make them clear that they should satisfy divergence free conditions. So you have to select properly. Otherwise, they will just violate nature. Something else will appear, not what you expect. Okay. So this is actually the example when you have full free. Sitting there, 2D gas. All right. Now, everything, all this preliminary work was done on that code, which we talked about. So this is the flagship Air Force code, developed by this book guy Thunder originally back in the 90s. A lot of work has been done on that. I can share materials, by the way, on these things because I have a lot of videos, and you can share. So this is a solver for the compressible unsteady on desktops. Strong conservative form, 6 order complex given, and second order implicit time matching, robust implicit simulation, efficient moving, parallel, everything. So we published a paper which I'll be talking about tomorrow. Remember that will be the SD70 full interactive with canonical abstract disturbance. It will whole presentation just about this topic because it's basically implementation of this specifically for the micro vehicle research. But in general, in this paper, we'll also take a label of things, including the momentum source for the gusts. That was in a journal, available journal. It's actually one of the longest papers. They were very complete. It's really thick, long. I don't know how many pages there. A lot of things there. So this is the stuff which I'll be talking primarily tomorrow. Again, we did the SD703 Air Full. That was originally where we implemented the whole source. This people project. That's why we actually have several top columns. Mark point 1, we understand 10, 60, and actually there will be another 100 that I had this one as well. So it goes in transitional regions. And we have this level separation bubble up here and everything else. And so this is actually for the turbulence with intensity of 0.7% of 35. Length scale, characteristic length scale here, number of modes which we use, and the specific duration. Now, the same program was formulated for the gust, with the time harmonic gust, the sharp edge gust, with the vortex, but that's a separate story. I'll talk about this later. So we compare first the results for the steady lifts and steady drag, and that was pretty good compared to the experiment, which was done on the return on. So that is, that's how these results look like. Like if you look at the time harmonic gust single mode of turbulence, you see that's actually a propagates. This is opposing here in the source. It goes like this whole wing section, right? And then it basically wipes through the boundary layer with the frequency of the gust. So this periodic wiping the boundary layer, you can see this whole process that passes through. You don't see the gust, you see this vertical structures of the boundary layer. You can see that due to this interaction, this is the process. So this is LES simulations. That's why we have this fine turbulence which shows up. It's well resolved, so everything is resolved up to the surface. Y plus value is 1. So it's very, very accurate simulation to see what's going on. This actually will be used later for acoustics, for the feedback loop interactions, because we did the same methodology. This code was perfect for those kind of things. Very powerful, very accurate. So that usually takes maybe 500 processors to run maybe for like several weeks sometimes. So usually what you do, by the way, if you do this simulation, let me just go this. If you do simulation on the airfoil and you want to resolve turbulence, you cannot do it 2 dimensions because there's no such thing as 2-dimensional turbulence. So you have to make extension, usually 0.1 or 0.2 record in the Z direction. So this is actually probably what 0.2 goes. So you can allow the turbulent structures to appear, and that's a necessity. You cannot do this you could do in RANS because you don't care. Then you can do 2D, but that will be nothing resolved. Don't do this. But if you want to resolve the real structure in the boundary layer, you have to do 3D. So this is an example of 1D time harmonic gas like this. You see, that was a process. Again, I'll talk about this more in detail. When they interact, it has duration of so many seconds, and it goes through, and it produces this effect of the see this gas boom started to appear. There's a lot of dynamics here. So of course, again, I'll talk about this tomorrow as well. So it's all MAV research, micro vehicle. So they were interested if something small, the small Reynolds number happening, you have the gust, like something in the air hitting this thing. What will be the effect on the aerodynamics? How much it will be responding in terms of lift, drag, moments, and particularly important how quickly it goes back to normal. The gas passes through. So the relaxation time was really important. But I'll talk about this more much later. We'll also talk about this problem because if you go from 1D to 2D, that's where you have to use what's called, what I mentioned, that's unsteady two-dimensional, second order three-fold theory by Tassi and Goldstein. So I'll talk about this tomorrow. So that's gonna get more complicated. This is actually the correction to the steady state solution, which is a series solution. This is a series. So you got this interaction with the gas. That's how it behaves. It's called the series spiral. It's something in this, and it's complex function. It's complex plane. Lift is complex because there's a S is a series function, but it's a complex function. So it takes care of amplitude and the phase at the same time. Because it's all about phase shifts in the solution. And when you go to 2D, then you have to account for this distortion. So distortion is account. You see, this is more or less straight. This is actually very distorted fronts. And that's a rapid distortion theory, which accounts for those effects as part of this theory. So I'll talk about this tomorrow. I'll just give you like a preview. Just keep in mind that's very important. You can account for the effect of camber, thickness, angle of attack. Original series result is all for the flat plate trigger. Like no angle, no nothing. And that's a classical series solution. Flat plate interacting with a single 1D transverse gust. Everything else beyond that will call this kind of corrections. And this correction will explained by this theory by Goldstein and Tassi back in the 79, I think. He published this paper in JFM. This paper is actually called IQ test for engineers. Really, I mean, try to understand it. Usually that's why people probably like dropping the whole profession because that was just crazy. You can look at the paper because I keep it just to kind of refresh your like mind. So you have to keep like your mind sharp just to kind of oh my god, okay, then you got this is really crazy, man, crazy. Probably one of the craziest you can imagine. Anyways, so now we're moving to 3D. 3D again, all this 2D stuff I'll talk about more. 3D is what will be interesting because it's actually the extension with Marina, CM Kazarian, Marina Kazarian. And that's about 3D effects because they have forward turbulence and forward directional response. So that was published in 2019 in San Diego first, extended in 2020. Comparison of 2D and 3D. So very interesting. So you have the span-wise component. So not just transverse and chord-wise, it's also span-wise. The span-wise component produces a very interesting feature, which we try to explore how this affects the turbulence response, because they all, of course, contain turbulence because all turbulence is smaller than 3D. So this feature is very interesting. Well, it shows how the 3D gas is generated using the same methodology. And the feature which numerical procedures. Oh, actually, by the way, she cannot walk on FDL 3D. She was Russian citizen, right? So you would have to use something else. So at that time, Peter, her husband, was doing open form. It was too much. She said no. She was doing fluid. Fluid was kind of something which is also possible to do, easier for sure, because it's actually very user friendly. Because do you use fluid?
Yeah.
Okay. So you can always get tutorials, you can get support, you can get the open form. You pretty much on your own. Yeah, then that's the thing. There are people who actually can provide service for you for money to explain what's going on. Because, for instance, Notre Dame, there's a professor, forgot his name. He actually originally from Serbia, I remember studying. But he actually his part-time job, he is a consultant for open form. So people like trying to do something, they call him. And I don't know what's going on here, and he actually helps. He's an expert, complete expert. So sometimes it requires expertise. You have some forums, of course, right? In the forums, you can probably ask questions, but who knows when they respond? And who knows who will respond? Is that if annoying? Anyway, so you see the progression for 2D Zhukovsky, we had like 30,000 cells. For 3D NACA 00 for the Ligas were 1.5 million. Then 3D the turbulence was 25 million. You really have to compress, have more grids because you have to put a lot of more modes, like 100 to 200 modes, which will require a lot of more stuff to resolve those frequencies. So you go into the high frequency content spectrum. Usually it's either uncommon spectrum or something like that, but you have to involve high frequency. The higher the frequency you have to involve, the more grid points you need to put to resolve, because typically, even with this 6-order time differencing, 6-order complex scheme, you need at least maybe 10 grid points per wavelengths to resolve it. Something like that. If you run something with open form, which is like 2D at best, it's like 25, 30. So you see, it should be like 3 times more mesh to run open form than this code, DL3DI, because it's 6-order accurate. So you need less point, but still a lot. 25 million. Okay, well, a lot. You know how much for the rotor we're running? Routinely, it's 100 million, or maybe even more than 500 million. So that requires all NASA computer systems, and that you run it for like months. So that's great. I mean, yeah, it's a different scale of the problem. So we're looking for quantum computer. Need to do something to this. So that's what happens. I mean, this is a beautiful problem. When you do 3D, what's called a plate cast, this is the wavefront. So you have this thing coming and interacting with a wing, say wing or the blade, right? So it's not just like this, it's interacted at the angle. So you have the component at an angle. Okay, so everything is governed by the convective wave equation, right? So this is acoustics. Acoustic is convective wave equation. Even in the case when you just forget about any kind of unsteadiness, you get Laplace, right? That's a classical invisible thing. Laplace equation has to be solved, get your, result even for like Joukowsky or something. But if you do acoustics, you always get the time term, which you have to retain, and this time term will bring you to the convective wave equation. So convective wave equation, we solve this thing in the frequency domain. So when you do frequency domain, convective wave equation converts to something called Helmholtz equation. And this is the Helmholtz equation right there. This is called Helmholtz equation. So you solve for phi, which is velocity potential function. So pressure directly relates to the dphi over dt. So once you get phi, you can get the pressure in a far field acoustics. That's how the system works. So if you think about that, if there would be like no K3, which comes from the 3-dimensional, right? There would be always a convective wave equation which produces wave, right? Real acoustic wave which propagates outside. However, if K3 appears, all of a sudden this thing can switch sign from positive to negative. You see, if K3 is larger than this big K3 is combination of K3 and beta, which is a square root of 1 minus Mach squared, right? Which relates to Mach squared, Mach number. And then K1 is this combination of frequency. So if for whatever reason, when you have K3, which is a 3-dimensional gust, you have this thing become a negative, all of a sudden it becomes elliptical. Do you know what the, okay, so there's something called hyperbolic equations and there's something called elliptical equations. So hyperbolic is classical equation which sustain propagation of waves. Like convective wave equation is classical hyperbolic equation. That's what you learn when you're going to CD. Then CD. Now, when you switch the sign, it becomes elliptical. Elliptical is like Laplace, the same thing. It has no propagation. Everything dies up very quickly. So it basically you don't sustain the wave. It doesn't propagate. It's immediately die. That's the evanescent wave. So it just starts, and then that's what the hydrodynamic pressure is responsible. Basically, it's satisfied this Laplace type of equation or this kind of equation with negative sign, which actually dies away the disturbance very quickly. It still will continue for some small lengths and then it dies out. This is still important. There's in rotor-state interactions, the evanescent waves still make, because they can actually reflect or refract into the propagating waves. But in this particular case, it doesn't happen. But the rotor-state interaction happens. So there's a lot of things there. That's why the two machinery is quite more difficult. No, in this case. Oh, you can say it's easier. It's not cases too. Anyway, so there's two different situations in chip here. K1 less than K3. It's called subcritical flow. Subcritical flow regimes. The equation is elliptic and it's exponential decay. That's what I'm saying. It's evanescent wave which is decay. So any kind of perturbation which appears doesn't propagate far. It's near field result. It's only in the near field. When you have supercritical, when K1, K3, that's a typical case for regular wave equation where there's no K3. That becomes hyperbolic and it propagates waves. So that's acoustics. You get the acoustics in far field. and there is a magic transition point. So this is actually shown in this diagram here, which is like a area of the subcritical versus supercritical versus Mach number. And this is I think lambda is another parameter which I forgot what it is here. But anyway, it's kind of like the angle between the K1 and K3, etc. So that shows that the regions in the spectrum, which can either propagate or have to decay in the wave number spectrum. Which is, think about that. If you have the spectrum of turbulence with three-dimensional modes, some of them will not propagate far away. Some of them die, some of them propagate. So it's always interesting to see which one actually will produce acoustic and which do not. So that's what was the original topic which I gave to Marina. Okay, figure it out. We have the turbulence. Some of them will propagate, some of them not. So you have to look at the spectrum in the end and compare with these predictions. We can do even analytically those things. So she was doing this thing. It was a bit of a killer for her. But some results I'll show. She didn't quite finish, but still. So in the case when you have this K3, you see if you look at the spirals for the unsteady lift, this is the measuring real part of the unsteady lift, which is the unsteady load on this side. So depending on the wave number which you get for the gust component, you can actually have either the result like in typical case like Sears result or Sears spiral, or you have that wiggle which will correspond to the transition from subcritical to supercritical. And this transition is usually shown. You actually can run simulations, or you can actually do the experiment. You'll find those things. These wiggles are coming from this transition from supercritical to subcritical regimes. Very interesting phenomenon. Small physics, but that's what people show. There was a guy with the name Graham who was doing a lot of analytical analysis of this thing back in the 70s. Because people were looking at this for a while, what's going on. But anyways, so in fact, this guy, he formulated this what they call analogy, where he said that the propagation will be, it depends on the transformation. You can actually transform the gas in a different frame of reference, like in a sort of plate for, the airflow frame of reference, in which case you'll find this is a sort of like analogous to the propagation of the gas of the swept wing with a Mach which will be the supersonic or subsonic. That's what basically corresponds to this. But with the transformation like this, you can get to this kind of swept wing problem where you have this supersonic or subsonic system in this particular case. So that was interesting. That was Graham's idea. So you can put this kind of thing in that analogy. And look it up. Anyway, so we started to compare with unsteady aerodynamic theory. Everything which we kind of figured about this thing. So we'll look at the results. She was running fluid simulations with Mach 0.5, 1D, 2D, and then 3D, and then with the spanwise. And then he compared against analytical predictions, which you pretty much get from solution of Kempfer's equation. And that's what we got. So everything is pretty much perfectly fine for these cases, which is pure hyperbolic, right? 1 and 2 gas, always hyperbolic. 3D gas, you see, that goes like boom. This change in the lift exactly corresponds to that wiggle in this complex diagram. This is real, but in the complex it has this wiggle. And that's what we get. We actually get a fluid solution, which matches pretty closely. Here is a bit of a different. I'm not sure what was causing. I never usually like fluid. Maybe that's the reason. But that's what it is. We actually confirmed that this process happened in the changing leaf calculus. And then there was artistic contours which you generate for this 3D gas. And then this analysis she was running. So this is acoustics now. So there was lift, that is aerodynamics. Now acoustics will look at the directivity gap with dipole. Directivity which predicts acoustic in the far field, depending on the situation, and this is all 2D and 1D. And then we'll compare actually against, for the real airfoil, you cannot compare with Sears anymore, because Sears is always flat plate. If you want to compare your predictions for the real geometry, the best you can get is something called GUS 3D. That's the method which was developed It's a visit solver, not quite CFD. Well, you can call it CFD, but it's very simplified and it's very fast. It's very, very fast. In fact, this is a solver which was developed by Jim Scott, which was a student of Otasi as well. Before me, he was also a NASA employee at the same time. He was working at NASA Glen. And he developed this code, gas ready. And in fact, that was the code which everyone was comparing for this category 2 problem for the CA workshop. That was the code which was supplying the correct solution. So it's very validated code. And you can see that in most cases we have some good results. Some cases do not quite match exactly. But by the way, this actually supposed to be a really good match in general, because people are happy when they match within like 340B. And 340B, it's actually a lot of like double or more. So that's actually pretty good match. Yeah.
How do you interpret the graphs?
So green is analytical, it's a CFD. And this is a validation. Gas ready is a solution it's a different code which we validate against.
But what does the shape?
It's dipole. I mentioned that. Dipole is what produced by unsteady loading. Acoustics produced by unsteady loading. They don't know what it is.
They haven't seen it.
Okay. I mentioned before,
They're waiting for your class.
it's a solution of light field equation. It's for acoustics. It's convective wave equation, right? It governs acoustics. So the solution of the acoustics is all about monopole, dipole, quadrupole. It's 3 cases. Monopole is what the thickness displacement. Quadrupole is turbulent stuff. And then dipole is unsteady forcing. So this unsteady forcing. So the gas produces the upwash, which is periodic, right? Because it basically has the angle of attack, which changes like this. You have the airfoil and this thing is like this. So every time it changes with the frequency of the gas, you have the unsteady lift, which changes like this. So unsteady lift, which changes like this, produces the acoustic field. And this acoustic field is right there. It's produced, especially shows up as dipole. So this is measured. Okay, how it's measured? You go from the airfoil center, some observer location, and to get this dipole, you basically go around the circle, full circle around, full circle, 360 degrees. And you measure the pressure at each of these things around. And that's what produces this thing. So that means if you're sitting right here, this is your airfoil, and you measure, like if you observe is right there, downstream of the airfoil, you will not hear nothing. It means that you see that zero, it's nothing. Like the effect is zero. But if you're sitting somewhere here, the effect will be here. Like it's still the same distance away, like 10 diameters or whatever, 10 chords, 100 chords. But if you're sitting in this direction, along this line, the airfoil, the gas, and somewhere here, you'll hear. That's what you'll hear there. If you hear, you'll not hear nothing. That's what it means. And that's basically what this dipole shows you. It's directivity pattern for the acoustic propagation. Okay. And that actually shows the steady pressure on the surface. It's PRMS, root square. For the pressure, and that's typical solution which you get for the steady pressure, which shows this for huge spike near the leading edge. That's the leading edge, and that's the trailing edge. So a huge spike near the leading edge when the gas just hits, and then everything decays towards the trailing edge, which is your cutter condition, things like that. So yeah, that's what the interpretation of this thing. And then we did the CL for 3D. So we get this E1. It's a gas which has no chord-wise, but it has this direction and this direction. It's like this. And so we model the gas with the K1 with the whole range from 2.6 to 4.9, like I don't know, 7. And K3 is fixed at 2. So the span-wise is fixed. And then you see what happens because you fix this K2, you cross the subcritical supercritical boundary when you go through, and this is the lift you get for all the sports. So you see, if your K1 is here, you're here. If your K1 is there, it's there. That's totally different from what you'd expect from the Sears theory for the pure 1 2-dimensional gas. So in 1 or 2-dimensional gas, when you increase K1, your amplitude always goes down. Which means that if you have the gas with a higher frequency, your lift will go down, and that's actually responds to the shear spiral. So shear spiral goes like this. So the higher the frequency, go along this line. Higher the frequency, the amplitude. This is the phase. So this is a complex plane. So this shows both the phase and amplitude. The radius is the amplitude. So this radius gets shrinking to basically nothing in the end, right? So if you have like very, very, very high frequency, the actual lift amplitude will be almost nothing, right? So that's what the shear spiral means. I think a lot of new things for you guys. Sorry. That's I'll say that. So that's what I do for this. And then we started to look at the superposition because we wanted to move to the turbulence. So we started first with the superposition of several modes. We see what the response will be acoustically. You see, like you have two modes. One is supercritical, the other supercritical. You see, the supercritical produces this red line. So that's acoustics. That's partial acoustics you get there. Subcritical, okay, it's there, but it's very small because it's decaying field. It's still there, you still hear it, but it will be decaying. The other will be propagating far away. See? Then we get more and more frequencies, and you can see all the supercritical frequencies here, all subcritical frequencies here. That's for pressure in the far field. And then eventually, whole point was, again, to superpose all the modes through the turbulence process, turbulence generation process. And this process is not straightforward. Sorry, the lecture is pretty complex, right? But this is actually even more, it's a different level of complex altogether. So synthetic turbulence generation procedure, STG, is basically employing this different methodology which people developed, right? Again, there's different methodologies like recycling, rescaling methodology, like classical methods like vorticity, small vortices with different sizes. We put them all together again to generate this. You can look at the literature, there are different things. Usually high computational cost, you cannot superpose it at the source, right? You want to have something at the source. Those usually happen when you put it in the upstream boundary again, but then everything dissipates. So you vector square one. So synthetic turbulence, that's what we have to do. You basically match your amplitudes and frequencies to something which is called random flow generation process, which will match the particular spectrum of turbulence you want to match, right? If you find an atmosphere, you have uncommon spectrum for your turbulence in the cloud somewhere. So that's what you're trying to match using this RFG procedure. So this is the methodology. Basically, this is what we have. This is what the turbulence, how the turbulence theory represents in terms of the summation of all harmonics. That's in a complex function plane. As you can see here, this is the turbulence, which has this intensity level, it's RFG, correlation tensor, the length scale, characteristic time scale, all these things. So we have to match them all. This is something which you either measure, you get from some other things. And so this is your turbulence spectrum. This is one-Kalman spectrum in terms of wave number, and this is like a one-dimensional spectrum of the intensity. So typically what you want to do, you want to create a process which will match the specific measured spectrum, could be one-Kalman, Gaussian, or Liebman. This is actually Gaussian. Actually, it's a simple form. There's one-Kalman, but there are other ones as well, depends on your specific application. So the RFG process is basically assembly of modes in a very special manner, statistically, to be able to match that particular spec. And eventually that's how it will look like. There will be some modes imposing, and a whole bunch of them will start interacting. So basically you impose a bunch of modes, like gusts, which I was talking about before. It's not just single mode. And they will they have to match the spectrum of turbulence which you meant upstream, right? So that's the idea. And this is what the random flow generation model works. It's actually a legacy from the work of Smirnov. It was very. Now there's another bunch of guys, also Russians. I don't know. It's very popular there. In St. Petersburg, they have a group of Travin and the Strelets, and they also collaborate with the guy very famous from Boeing, which is Spalin. They usually work together. For some reason they love each other. So I'm not sure how they could collaborate now. Oh, Spalin, I think, retired now. So it's no problem because in these days it's difficult. But used to be they would work together. So this guy and this guy, they develop independent different processes, how you do this random flow generation. This is all down here. You can see through these tensors, permutation vectors. You basically generate an intermediate randomly fluctuating velocity, which is constructed in this particular form. And you have those permutation tensors for all these amplitudes, for the frequencies, everything else. So that's, if you match them all together, you can match it to the spectrum which you impose. Like, for instance, Gaussian spectrum is right there. That's the energy spectrum from Gaussian turbulence. So you can get this thing, put in here, you generate all these amplitudes, frequencies, which will match it. Works like magic. It's a pure math, statistical analysis, but it works like this. So given those scales, which are given for the turbulence, you and the energy spectrum, the envelope of the energy, you can generate necessary harmonics. You need to match those harmonics to the process which we do for the source for each particular gas, because as I say, has frequency, has the amplitude, same process. So it's exactly. So you have generation process, and then you have another generation. It's generation of your flow field which you want to match now based on the turbulence which you have. And then you have generation in the source mode. Okay, so it's two-step. Anyway, so the velocity to the scale, there's a lot of things there. It's a bit of crazy stuff, but you can do both isotropic and anisotropic turbulence too. Yeah.
Is that a kind of nose that you apply?
Huh?
Is that a kind of nose that you apply?
No?
Or just, nose, or just random flow?
No, it's the flow is measured.
Okay.
So you have measurements which will produce for you this kind of things. Like this is what given L, T, and intensity. You can generate this based on this and based on the profile of your energy spectrum, which is could be on Karman, Gauss, etc. So given those things, you can match. That's what we do. So this is the original papers which were doing this RFG. So RFG is done by the people, and we just match what they produce with our source model. So the second step. That's what that's Maria was very careful to put all together. So you have normalized amplitude of that in the morning, direction of the wave number, phase, non-dimensional frequency, and then you generate wave numbers and frequency representing a sample of random turbulence energy spectrum, which is given, and then this Tversky decomposition is also introduced. So the latest version of this methodology, again, is developed by the guys at some point. This is the guy. See, Shu, Pollard here, and Strelets, and Trivan. These three from St. Petersburg University. And Pollard, of course, is Boeing guy, very famous, Pollard on Mars. So they all work together and generate this kind of methodology. Turbulence generators for advanced LES interfaces and zone oscillations. So that's what was published. You can look at this particular reference back in 2014. Was the latest from them in the Flow, Turbulence, and Combustion journal. And then there was a previous site, kind of the same thing, by Adamian and Trivan. So the same Trivan is pretty much I think I talked to this guy at some conference when they were still allowed to come to AAA. None of them are allowed anymore. So, but it used to be that they were there all the time. It used to be all sessions in AAA conference. Like you would go to, like in Washington somewhere, there's a huge, like 3,000 people AAA meetings, and then there will be sessions on like nuclear physics, all Russians. And I remember the American guy would open the door, come in, and it was the Russian session. He would like run away. And some departments, like in physics and some universities, they all like almost 90% Russians too, over there in the US, especially in fundamental physics. Right here, a lot of the Russians there. So that's what you had the legacy, right? In Columbia as well, from Shibeshin, with guys who actually taken all the degrees from Russia, coming here to teach. Yeah, we had a lot of international presence. Last time I was there, well, 5 years ago, there was nobody, but there was one Indian guy in the whole department, and he would like take him everywhere by hand, to like all labs. You'll be one single guy. Poorly, feels like scared everywhere. The other friend. Anyways, so this is methodology. And then you have this STG procedure, which how you generate the modes. Actually, numerically, it's quite complex. You have to do a lot of wave numbers uniformly distributed on the surface sphere, like the EM direction should be orthogonal to wave number direction. There's a lot of details. Believe me, I mean, she was suffering a lot. She didn't like that much, all those things. She told me before later, but, I'm not a PhD material. No, but she got it. She graduated, but she works with a diesel company now, Cummins in India. It's totally different. Actually, like managers, technicians there. It's very far from everything. But she's got a baby just found, so she's got get it on. So fluid analytical, that's what the eventually gets result. For leaf spectrum, for time history of it was pretty good. So that's what we get from all this analysis. And then we'll look at the. So we can predict now from turbulence based on this analysis which modes are supercritical, which subcritical, which actually propagate into acoustics, and we were matching these results to the spikes she measured. So indeed, it was actually proving the point that this supercritical transition happens, and it's in turbulence. Not all modes can actually create acoustics. Only few, which actually correspond to the spikes, are the ones which are supercritical modes. So that was nice, very nice final result. No matter how she hated all this mathematics, but we got it. But yeah, it was fun for pressure. Match again. All right, that's it. Thank you. If you have any questions, it's a bit more complicated topic today than before, but hopefully you can get through. Right. A lot of new knowledge.
Okay.
I have a question. The pressure disturbances are generated by the ordinances of the cast or
Pressure disturbances also, in all cases, in this case, is generated by interaction of the vortical disturbances with the structure. When you hit the airfoil, that's when acoustics is generated. By themselves, they don't generate any acoustics, any pressure. They're not supposed to, at least.
those pressure disturbances can also like acoustical modes, like the first initial.
Yeah, that's it. That's
right.
It's called transition. It's or reflection called or scattering. Yeah, it's called scattering problem. All this thing is called scattering, acoustic scattering problem. That means that you have the vortex interacting with the vertical disturbance, turbulence, interacting with something, and this vertical disturbance scatters into acoustic waves when it interacts with the solid. Yeah, with the blade or airfoil wing, etc. So that's a scattering problem. Or leading edge problem, by the way, also. It's called leading edge problem.
Basically, I want to know with besides all these projects related to aerodynamics with a onshore dynamics. If you got also projects like related to structural analysis, like structural analysis of spacecraft.
Yeah, no, we don't do it because it's too simple. Structural analysis is nothing compared to this. I mean, we always look at the people who structures like you.
I have to tell you that the guy who masters fluid mechanics, masters everything. So it's basically like fluid mechanics is the dad of fluid mechanics.
Yeah. Fluid mechanics, fluid mechanics. You have too many degrees of freedom there. Sorry. That's it. Fluid can be everywhere. Fluid is liquid. Much more complicated. Well, I'm kidding. I mean, it's some problems which I call quite complex. I know that's in solids as well. Yeah. But we do solids only in application, like for instance, this smart material stuff.
Yeah.
That could be like some application. First time we try to do this. Well, you can say, would you consider flutters as kind of solid? I'm not sure. It kind of spring, which produces flutter response. So you have structure. There's a structural response. We call it structural. Aeroelasticity. Aeroelasticity is an example of the structural analysis. Because you have structure interacting with still fluid. You know, but it's a aeroelasticity, which is kind of different.
General question. How do you go about implementing this in other simulations? Because this is a model, right? So how do you take this and use it for other more complex analysis or aircraft, for example?
But we do it all the time. That's what we do for rotors. I will show you tomorrow. For tomorrow, it will be about rotor applications of these methodologies. That's what Vladimir is doing. So we put this gas, the turbulence, etc., upstream of the rotor, depending on this orientation, and we see how this whole rotor will behave in turbulence. So near the vertical.
So at the end, so like very complex because it's like the derivation, but it ends up being like a simple equation which you could put in a solver.
That's what we do. We have a source implemented as a user-defined function. In any of those codes, OpenFOAM or DLPDI or Fluent, that's what you get. In all the codes which we work with, and now Overflow, NASA codes now. NASA specifically asked us to work on this. In fact, on Monday, I have to see because I have a meeting with NASA people by Zoom on Monday. And this will be actually regarding my student who now has his pathway fellowship, and they want us to discuss his PhD project. And one thing, because they developed brand new NASA code, brand new, it's called Lava. I'm not sure what exactly it's doing. It's probably some new methodology. But the first thing they probably would like us to do is to implement this thing in the code. So that's one of the biggest things.
How much computational demand does it take to run compared to an overall dedicated?
Well, you need to resolve, but that's anyways you have to resolve because you need to resolve propagation. But then you need to resolve acoustics. This is acoustics problem, right? So you have this interaction scattering problem. So you need to resolve all the way from the point of this thing generation to the point of interaction, but you need to resolve acoustics as well. So you always look at the wave cutoff frequencies, and cutoff frequencies will be determined by the grid resolution. So that's how you determine the grid, and the grid will determine the complexity of the simulation, how much time it will take. So it all depends on a specific situation. But for rotors, could be millions and millions of grid points. So that's why it takes forever. Even though they have like 500 nodes. We run on zeros nodes, it's still going on.
So this is also this lecture is a motivation for professors to next class on aeroacoustics. So let us remind our school and the head of school register this aeroacoustics class.
Well,
So-
who's teaching that?
I can feel.
When? Just tell me when. Tomorrow?
Next semester of next year.
Okay, yeah, of course, yeah. Not next week, that's
So, but I think you have understood the relevance. So, really get involved into aerodynamics, viscous flow, aeroacoustics. Because if you want to apply these things to practical aerodynamics, also because that one.
Yeah, that's definitely. I'm preparing right now for the fall. Rotorcraft aerodynamics and acoustics. That's what will be like what my Kindle used to do at CF. But now I'm adding a lot of acoustics. And that's a legacy class from Richmond.
And there any other questions? That's it.
Thank you.
Thank you.
So we have one more in the afternoon, right?
Yeah.